Okay, hi everybody, I'm Daniel and I'm going to be explaining how to do problem number 10 from the Washington Gold TST for this year. So, the question reads, so we have this convex pentagon ABCDE that has all side lengths equal. So if it has all side lengths equal, then we can try drawing a pentagon with all of its side lengths equal. So let's just try to draw one right now. And it might look something like this. Okay. And so we know that all of these 5 lengths are equal. So now it tells us that the internal angle bisectors of angle BCD and CDE, which are these two lines, right here and right here, they should meet at a point P on segment B. It says suppose P lies on segment BE with BP equals 11 and PE equals 15. So now we need to find the area of ABCDE. So we got a bit lucky here. The diagram looks about right. But one thing that you can kind of notice here is that A is kind of hanging up here. It's not really doing that much. We could really just erase A from the diagram completely, although I'm not going to do that. I'm going to kind of let you guys see that if you kind of erase A from the diagram here, the rest of the diagram is pretty independent. And once you determine what the rest of the diagram looks like, then you can kind of just tack on the isosceles triangle at the top to determine where A is. And now it's asking us to find the area of the pentagon, but for right now, we're just going to focus on finding the dimensions of the pentagon first. So one thing that we know are that these two angles are equal, and we also know that these two angles are equal. Okay, and now one thing that you might look at when you see this problem is that you might be confused at is this P lies on BE condition. This P lies on BE condition is pretty tricky to look at, especially because you don't really know what to do with it. But the thing is, we don't really need to start from the P lies on BE condition exactly. If you look at the angles here, you know that both of these angles are equal, and that means that you should be able to do something with them. Whenever you have equal angles and equal sides, you should try to look for similar or congruent triangles. And if we try to do that here, we can see that we actually end up with a few. So right here, if you guys remember, SAS congruence tells us that if there's two sides and an equal angle between them, on two different triangles, then we should be able to have two different congruent triangles. And in this case, BC equals CD, CP is itself, and the two angles between those two corresponding sides, these two pairs of corresponding sides will be equal, and as a result, we have the triangle BCP is congruent to the triangle DCP. There are reflections across the line CP. And using the exact same logic on the other side, we see that since DP is itself, CD equals DE, and these two angles are the same, we can actually do the same exact reflection over the angle bisector again. We get angle DEP is also similar to these two. So just take a moment to look at this, and you can see that, well, if you kind of just reflect this kind of whole triangle right here, this whole thing, if you reflect this whole triangle over to this side, then you should be able to get the exact same triangle on the other side. And same thing if you reflect this triangle over the line DP. So these three triangles are all congruent, and what this tells us is a few things. So first, it can tell us that the side lengths corresponding are equal. So if we just look at the side lengths corresponding, we see that BP should equal DP. And this tells us that DP is 11. It also should tell us that EP equals CP. So it tells us that CP equals 15. So DP equals 11 and CP equals 15. And what else does it tell us? Well, other than equal sides, it also tells us that the lengths corresponding are equal. I mean, the angles corresponding. are equal. So if we look at the angles, especially specifically the ones that we haven't really looked at yet, the ones we have looked at yet, I guess, are this one. This one should be equal to these two, and this one should be equal to those two. But what we haven't looked at yet are the 3 in here. And in fact, the 3 in here should all be equal to each other, because if you look right here, CPD and CPB are corresponding angles of the two triangles. So if all 3 of these are equal and they add up to 180 degrees, then we know that all 3 of them will equal 60 degrees. So now we're actually getting somewhere. So since we have these 60-degree angles, then we basically determine the whole structure of the bottom part of the pentagon. So what we can do here is, once we have this whole bottom structure, then we can kind of find the length of the pentagon, the side length of the pentagon. So how do we do that? We use law of cosine. So law of cosine should tell us that the length of BC squared should be equal to CP squared plus BP squared, and then minus 2 times the cosine of, sorry, I forgot to write here that it is 60 degrees. We mentioned this already. 2 times the cosine of 60 degrees, and then times CP times BP. So we have these two lengths, CP and BP, already, because CP is equal to 15 and BP equals 11. And so this should tell us that BC squared is equal to 11, or 15 squared plus 11 squared, and then minus this 2 cosine 60. Cosine 60 is 1/2, so this actually just cancels out to 1. We can just ignore this, and this is minus 11 times 15. And if we evaluate this out, we just get BC is equal to the square root of 181. Okay, and what else can we do? So let's make a split right here. Once we've done this, we can actually also try to find the area of this triangle BCP. So if we want to try to find the area of the triangle BCP, all we need to do is just use a sine angle formula. If you guys recall, it's just the area of BCP will just be equal to 1/2 times the sine of 60 degrees, and then times 11 times 15. And this should be equal to root 3 over 4. And as a result, we should get this is equal to 165 root 3 over 4. And so all three of these areas have 165 root 3 over 4 area. So all the bottom triangles are congruent, and that's why they all have the same area. And now all we need to do is calculate the area of the top triangle. And to calculate the area of the top triangle, you might already notice what's going on, but you might already notice what's going on, but if you notice what the top triangle looks like, we can actually just redraw it over here. It's an isosceles triangle, actually, and we have all the side lengths of the triangle. So it kind of gives us already that, if we look over here, kind of gives us already that BP is 11 and PE is 15. So it tells us that the bottom length should be 26. And over here, we already have the side lengths. They're both root 181, as we found from earlier. So now, once we have this, we have the whole isosceles triangle, and we can just calculate the area just by dropping the altitude to what we can call M right here. So the M should be the midpoint of the side BE, and that means that BM is 13. And as a result, we should get that by Pythagorean theorem. We have that AM is squared is equal to 181 minus 169, which is 13 squared. this goes that it is 11. So AM should be equal to 2 root 3. Once we have that AM is 2 root 3 and we have the base, then we can just do 1/2 times base times height, and we should get that the area of this portion is the area of ABE is equal to 26 root 3. Okay. And since we have this area is 26 root 3, we can mark that over here. So we have this kind of area is 26 root 3. So now we have one thing that's 26 root 3 and 3 things that are all root 165 root 3 over 4. And to calculate the final area, you simply need to add those 4 triangles areas together. And to do that, we can just do 1 times 26 root 3 and then multiplied by, should just be multiplied by, or we should just have to add 3 times 165 root 3 over 4. And our final answer should be equal to, our final answer should be equal to 599 root 3 over 4. After a little bit of calculation, you just need to put a common denominator, and that's your final answer.